Let's explore how linear algebra can be applied to principal components analysis. PCA is frequently used in data analysis and artificial intelligence, and it's one of the methods of dimension reduction. First of all, let me explain why we need dimension reduction in artificial intelligence. First, we compress high-dimensional data to lower dimensions. Additionally, by reducing the dimensionality of the data, we eliminate noise within it. In a sense, we reduce the data dimensions from n to m, where m is less than n, through dimension reduction. However, we cannot randomly eliminate any dimension in the data. Instead, we retain m meaningful data while discarding n-m meaningless dimensions. For example, if the data is three-dimensional, we keep two meaningful dimensions and eliminate one unnecessary dimension. However, when eliminating unnecessary dimensions, instead of simply discarding them, we transform the coordinate space before elimination. PCA is a method of dimension reduction that eliminates unnecessary dimensions within the transformed coordinate space. So, how do we determine which dimension is meaningful and which is not? First, we start by normalization. Suppose we have data x. To normalize the data, we subtract the mean of the data first, and then divide by the standard deviation of x. Why do we need to normalize data? If we examine the dimensions of the data, we may find that some dimensions have a range between 0 and 100, while others might range between 0 and 1, or negative 100 to 100. However, some dimensions with a range between 0 and 1 might be more important than those with a wider range. Thus, by normalizing the data, we can standardize each dimension to have a range consistent with the standard normal distribution. Step 2 involves calculating the covariance matrix. We utilize the formula displayed on the screen to derive this matrix. From step 1, we have normalized data. When we examine the normalized data more closely, we find that some data fluctuates with short cycles, while others change slowly with longer periods. Some data may even fluctuate more rapidly with shorter cycles than this. We regard rapidly fluctuating data as meaningful, while data with slower fluctuations are deemed unnecessary, as they convey less information. The covariance matrix not only contains information about its own variance, but also the relationships with other n-1 data. For instance, consider data number 1 and data number 2. Let's visualize the variances of these datasets. Given that both datasets fluctuate with the same cycle, we might question the necessity of retaining both datasets rather than utilizing just one of them. Suppose we have a covariance matrix V. After we find the eigenvalues and eigenvectors of this matrix, we can decompose it using matrix diagonalization. In the matrices P and D, which contain the eigenvectors and eigenvalues respectively, we can find information about the variances of the data, since the covariance matrix shows how data relate to each other. As mentioned earlier, we can identify pairs of data that exhibit similar patterns using the covariance matrix. Using the eigenvalues from matrix D, we can determine which data is important and which is not. A high eigenvalue signifies important data, while a low eigenvalue suggests less significance, indicating that we might consider dropping the corresponding data. In the matrix D obtained through matrix diagonalization, we have n eigenvalues from lambda 1 to lambda n. When arranging the eigenvalues in matrix D, we order them by their magnitude. Within matrix D, we retain the top m eigenvalues while discarding the rest, as higher eigenvalues indicate greater significance. We also have matrices P and P inverse surrounding matrix D. Similarly, we preserve only the first m eigenvectors with highest eigenvalues from these matrices while discarding the rest. This process reduces the data's dimensionality by retaining only the most important components. Now let's see how the dimensionality of data can be reduced. The dimension of the reduced matrix P inverse is m by n, while the dimension of our original data matrix A is n by n. By multiplying matrix A by matrix P inverse, we obtain a new matrix A with reduced dimension. To summarize, PCA is one of the important examples of applications of eigenvalues and eigenvectors, and it's frequently used in data processing. So remember how eigenvectors and eigenvalues are applied to other fields outside of linear algebra. Now, we're going to explore matrix exponentials. Although matrix exponentials don't appear frequently in image processing or natural language processing, their significance in understanding a random walk or Markov decision process, which are decision-making processes. So it would be beneficial to learn about matrix exponentials. Suppose we have a matrix with entries 1, 2, 3, and 4. The exponential of the matrix is not a matrix with values e1, e2, e3, and e4. The definition of exponential of matrix A resembles Taylor's theorem. The mathematical definition of a matrix exponential is written on the board. Its mathematical definition is entirely different from exponentiating each individual entry. Matrix exponentials have the following properties. Let's explore each property in detail. The first two properties are similar to the properties of scalar exponentials. However, the third property is especially important. Suppose the function f of x is e to the x. Then the derivative of f of x is also e to the x. This property holds for matrices as well. When A is a matrix, the derivative of e to the at is just a times e to the at. Because of this simple property, we use matrix exponentials often in AI paper. Our last property is also very important. When we decompose an exponential of a matrix with matrix diagonalization, every matrix stays the same except for the central matrix, meaning that eigenvectors don't change. We often use matrix exponentials when we want to find the solution to linear systems. Suppose the values of x of t vary with time, and they are also influenced by the velocity. We define x of t as a naught times the exponential of at plus b. Then the derivative of x of t is a naught times the exponential of at. If we substitute a naught times exponential of at plus b into x of t in the formula above, we get a naught times exponential of at plus ba. Thus, ba equals 0, and we can drop b in x of t. Therefore, x of t equals a naught times exponential of at. To summarize, when we want to observe changes in values over time, the solution of the linear system often involves a matrix exponential. The last topic we'll cover today is the pseudo-inverse matrix. Let's consider a matrix A and a vector B, where their relationship is represented by a matrix vector multiplication. If we multiply both sides of the equation by the inverse of matrix A, we get X equals A inverse times B. However, if A is not a square matrix, meaning it's a rectangular matrix, then the rank of A is less than n. Consequently, the matrix doesn't have an inverse. For instance, if vector X is in Rn, and vector B is in Rm, matrix A is an m by m matrix, and it doesn't have an inverse. However, even though the rectangular matrix A doesn't have an inverse, we can determine its pseudo-inverse matrix. Instead of multiplying the inverse of A on both sides, we multiply the transpose of matrix A. Initially, A is an m by n matrix, X is a vector in Rn, and B is a vector in Rm. The dimension of the transpose of matrix A is n by m. Thus, we can write n by m times m by n times n by 1 equals n by m times m by 1. The dimension of the product of these two matrices is n by n. So we can determine an inverse of the product. This time, we'll multiply the inverse of A transpose times A on both sides of the equation. The dimension of the inverse of the product is n by n, and the dimension of A transpose is n by m, and the dimension of B is m by 1. Thus, the dimension of the final product is n by 1. Does this final product provide a complete explanation of vector X? It depends on the sizes of m and n. Suppose m equals 3 and n equals 100. Through the matrix vector multiplication, the dimension of X has been decreased from 100 to 3, which means the information contained in X has been compressed to a lower dimension. And during the process, some information can be lost. Thus, complete recovery of information would be impossible. X will partially recover its information as much as B can explain. However, when m is much larger than n, B contains much more information than X, meaning that X can completely recover its information. Pseudo-inverse matrices are commonly used in AI research papers, so it's worth noting the concept of the information recovery process with pseudo-inverse matrices. So far, we have covered various topics in linear algebra, but there's one very important key point you must remember: the geometric meanings of the concepts. Throughout the lecture, we explore the geometric interpretations of matrices, inverse matrices, rank, determinants, matrix vector multiplication, and so on. We also learned about their applications in neural networks and the attention mechanism. A significant part of linear algebra revolves around matrix multiplication, or multiplication between matrices and vectors, which are commonly used when building AI models. We also learned about transformation of space through matrix multiplication. With matrix multiplication, we can not only rotate or tilt space, but also increase or decrease dimensions. Moreover, if the inverse of a matrix does not exist, information can be lost during the transformation process. Understanding these geometric interpretations of concepts is crucial when developing your own AI models or reading AI research papers. While you can review linear algebra by solving problems in textbooks, I highly recommend picking an AI research paper and trying to understand how the geometric meanings of the concept we've learned in the lecture are applied. That's it for today's lecture, and thank you so much for listening. See you at the next lecture.